So we have been talking about how to take a polynomial, factor it, and then once it's in factored form to solve it, right? And we've kind of beaten that horse well into the ground. We've talked about everything that we have to talk about in this kind of a course in that regard. I have just one idea left to talk about for this chapter, and that is how to go from like a description of a polynomial to a polynomial. So we have all the tools we need to be able to do this sort of thing. So today all we're going to do is look at some examples of kind of how to do this. And I'll explain kind of the tools that we're using along the way to do these sorts of things. But it's all things that we've already talked about and developed. We're just going to apply them in a slightly different way. So we're going to write a polynomial that meets the criteria, 1, it has factors with integer coefficients. And has the solutions 1, 1, 1, and square root 3, and then has a minimum degree. Okay. So let's start with that we need to have integer coefficients. So if we want to have integer coefficients, we need to make sure that we are following the irrational conjugates theorem and also the complex conjugates theorem. Let me remind you what those two things say again. So a polynomial with integer coefficients has irrational solutions if and only if those irrational solutions occur in conjugate pairs. So if I look at, or the way I'm going to apply that is I'm going to look at my list of solutions, and I'm going to look for any irrational numbers listed there. Do we have any irrational numbers on our list of solutions? We do. The square root of 3. So if the square root of 3 is included, I also need to include its conjugate. What is the conjugate for the square root of 3? It's negative square root 3. So conjugates always have the opposite sign in front of, in the case of an irrational conjugate, the irrational part. Okay. The complex conjugates theorem says a polynomial with integer coefficients has imaginary solutions if and only if those imaginary solutions occur in conjugate pairs. So now I'm going to look at my list and look to see if there's any imaginary solutions on my list. Are there any imaginary solutions on my list? No. So we don't have to worry about that anymore. Okay? So we're done with that first step for now. We're going to have to come back to it in a little bit, but we squeezed out of this what we needed to. Now I'm going to move on to this piece of criteria. And what I'm going to do is I'm just going to write down these 5 solutions. What I'm going to do now is I'm going to make them all equal to 0. So the first one, I'm going to subtract 1 from both sides. And then I'm going to subtract the square root of 3 from both sides. And then I'm going to add the square root of 3 to both sides. And what I did is I've converted those 5 solutions into 5 equations that are all equal to 0. Everybody's okay with what we've done? Now, if I multiply all 5 of these equations together, I'm going to get x minus 1 times x minus 1 times x minus 1 times x minus root 3 times x plus root 3, all is equal to 0. So what I have now is the factored form for a polynomial that has those 5 solutions. Guaranteed, right? Does everybody follow on that? Now I'm going to circle back to that first bullet point here that says the factors have integer coefficients. If I go down and I look at those 5 factors, do I have integer coefficients for all of them? Well, those 3 all have integer coefficients, but the last 2 do not, because the square root of 3 is not an integer. So the way that I can deal with that is these 2 conjugate pairs. I'm just going to multiply them together. So to multiply those together, I'm just going to FOIL them out. So now that I've FOILed this out, I'm going to combine my like terms. Notice I have a positive x root 3 and a negative x root 3. Those are going to add to give me 0. And then I have minus the square root of 3 squared. What is the square root of 3 squared? Just 3, right? Square root of 3 squared is 9, and the square root of 9 is 3. Or you can think about the square and the square root just kind of canceling each other out. So what I'm left with then is x squared minus 3. So there's my polynomial. All the factors have integer coefficients. I know I'm going to have the solutions 1, 1, square root of 3 out of it. And the minimum degree part, because I didn't include anything extra, I know I've satisfied that part. So the minimum degree just means that, like, oh, I don't know how many times I should include this. Maybe I'll just include it 100 times or something. Like, you don't do anything silly like that. Okay? Do we feel okay about this? Let's try another example. Okay? The process is going to remain more or less the same, but some weirder things can happen. So let's look at some more examples of things. Actually, I'm going to make that a 1/2. So let's say I want to write the polynomial where I have has factors with integer coefficients, has the solutions 1/2, 2, 2, and 3 plus 5i, has a minimum degree, and a leading coefficient of 6. So I'm going to start here using the irrational conjugates theorem and complex conjugates theorem. And I'm going to check my list of solutions. Do I have any irrational numbers on my list of solutions? No, right? I don't have any square roots anywhere in there. Do I have any imaginary numbers on this list of solutions? Yes. 3 plus 5i is an imaginary number. So I'm going to also need its conjugate on my list. What will the conjugate of 3 plus 5i be? It'll be 3 minus 5i. Everybody okay there? Now I'm going to take these solutions and convert them to factors. What factor is the solution 1/2 going to give us? X minus 1/2. What solution or what factor will x equals 2 give us? X minus 2. And because there's 2 of them, I'm just going to write x minus 2 squared. Notice I'm cutting out a little bit of the work that I did at this step from the first example, right? I don't need you to show that work, but if I don't show you how I did that, doesn't make a lot of sense of what I'm doing right now. Everybody's okay still? Here I am going to write this step out because it makes it a little bit easier to see what I'm going to do. So rather than subtracting the 3 and the 5i separately, I'm going to subtract the entire thing. I'm going to treat it like one quantity. And similarly, I'll do the same thing here. You'll see in a moment why that makes life a little bit more convenient, but it makes the multiplication step a little bit easier that we're going to do in a minute. You don't need to do it that way, but my suggestion is that it makes life a bit easier to do it that way. Okay. So now let's go back to the first and check to make sure all these factors have integer coefficients. We already have a problem with the first factor, right? X minus 1/2. That doesn't have all integer coefficients because 1/2 is not an integer. So what can we do to fix that? What can we do to that factor to change it so it has integer coefficients? Could I multiply it by something? If I multiply it by 2, what's going to happen if I multiply that factor by 2? I'd get 2x minus 1. Oh. Okay. That seems like it does it then, right? Did I change the solution at all by doing that? No, when I set that equal to 0, I'm still going to get 1/2 as my solution. So it's perfectly fine to do that. Everybody is okay? And these two definitely don't have integer coefficients because I have the I in there. So I'm going to have to FOIL that out. So when I do the foiling, again, I'm going to think about these guys as one thing. So I have x squared minus x times 3 minus 5i minus x times 3 plus 5i plus 3 minus 5i times 3 plus 5i. So now I just need to multiply some things out. So I'm going to distribute the x through. And then I'm going to FOIL out that last pair. Okay. Boy, that looks pretty gross and messy there. The good things is, if you look carefully, there's a lot of like terms that are going to cancel each other out there, right? I have a positive 5i and a negative 5i. I have a positive oops. Those are supposed to have x's on the end also. 5ix. And I have a positive 15i and a negative 15i. Those are going to cancel out. And then remember, I squared was something. What does I squared equal? -1. So if I go and I combine my like terms now, still have the x squared. Minus 3x is minus 6x. Then I have 9 minus 25 times -1. Well, 25 times -1 is -25, and minus a negative is positive. So 9 plus 25 is 34. So we're good there. Now we have all integer coefficients. Let's go back and check our list. We have the minimum degree part handled because we didn't do anything extra. Leading coefficient of 6. What is our leading coefficient right now? It's 2. You can tell because the leading coefficient is just going to come from the product of the leading terms of the polynomial factors. So the leading coefficient right now is 2. I need it to be 6. So how can I fix that? Multiply by 3. And we're good. Everybody okay there? Okay. So notice on this one, we got this really kind of gross foiling problem. That happens specifically when you have like 3 plus 5i, where you have a real part and an imaginary part. It would also happen similar if you had like 3 plus square root of 5, where you have a rational part plus or minus an irrational part. Got to be careful on those big FOIL out ones. It's tough, or it's easy to make a mistake because there's a lot of multiplication involved on that. But all right, let's do one more example and we'll call it good for today. So the polynomial we want to write has factors with integer coefficients, solutions of 3, 3, 3, 2i, and then 1 minus 2 root 3. Has minimum degree, and then no constant term. So again, we'll start here and apply the irrational conjugates and complex conjugates theorem. So I notice that here I have an irrational part. So I'm going to need its conjugate. And here I have an imaginary part. So I'm going to need its conjugate. Everybody okay there? I'm then going to convert these into factors. So I have 3x minus 3's, and x minus 2i, and x plus 2i, and x minus the quantity, 1 minus 2 root 3, and an x minus the quantity 1 plus 2 root 3. Notice that I wrote the conjugate pairs next to each other, because the next thing I'm going to do is multiply them out. So in each of these cases, I need to FOIL. Okay. So those two cancel out, and I remember that I squared is -1. Here I have some more multiplication to do. So I'll distribute the x's and then FOIL out the other part. Okay. So if I go and I combine some like terms, I have a negative 2x root 3 and a positive 2x root 3. Those will cancel out. I have a negative 2 root 3 and a positive 2 root 3. Those will cancel out. And I know the square root of 9 is really just 3. And if I combine my like terms now, I have x squared minus 2x, and then a 1 minus 12. Well, minus 12, 1 minus 12 is minus 11. And we have one more piece of criteria to worry about, right? So we did this, we didn't do anything extra. No constant term. Let's look at what we have right now. What is our constant term going to be right now? It's going to be 27 times 4 times 11, right? Actually, negative 27 times 4 times negative 11. Everybody can see that? Again, remember I can get the leading term by multiplying the leading terms. I can get the constant term or the trailing term by multiplying the last terms, right? however I multiply that out, I know I'm going to have to multiply all the firsts together. That'll give us the biggest degree thing, and all the lasts together. That'll give us the lowest degree thing. So just to put a number on it, 27 times 4 times 11 is 1,188. Right? So that's what we have. What we want is something that looks like this. Some stuff. My last term is something with an x on it, and then plus 0. Right? Everybody's okay there? So what can I do to this to make it look like that? Any ideas? It's not entirely clear, so any guesses are fine. We have something that looks like this. We want it to look like that. What can we do? If we just do this, that gets rid of the constant term, right? Oops. Yeah, that gets rid of the constant term, right? Now, is that what we want to do, though? That messes something else up. If we do that, what does that mess up? This is a really important question. What did we lose from our criteria by writing minus 1,188 there at the end? We lost all of these solutions by doing that. Because remember, if I set this equal to 0 and solve, I no longer can set each factor equal to 0 because I don't have multiplication all the way through. So we definitely don't want to do that. That's not what we need to do. So adding and subtracting something at the end is going to be out, right? That's going to be a bad idea. What are we left with? Divide or multiply. Okay? So is there something we could divide or multiply this by? So I have something that ends 1,188, and I want it to end with something, some coefficient. It doesn't matter. It could be 5, could be 7, could be 13, negative 56, 10,142. I don't care. But then x. Is there something I can multiply this by so that it ends with an x? X, right? If I do that and I distribute it all the way through, it's going to end with 1,188x. And because we've multiplied, when we set this equal to 0, did we lose any of our solutions? Nope. We only picked up an extra one. We picked up x equals 0, but that's fine because we need it to be there to get rid of the constant term. So it's not like it's violating the minimum degree part. So that's it. So to get rid of a constant term, we just multiply by x. Very good. Okay. So that's that.